Okay, let's continue with the discussion of stored energy. So you guys had some questions to answer in class. Where else can you store energy? And one of the ideas was that a spring stores energy. So when you stretch a slinky out, energy is stored in the coils as you displace them from one another. When you let go of the slinky, that spring potential energy becomes kinetic because the slinky or the spring will pull itself back in and give each piece of the slinky a velocity. So we see something here called the work done by gravitational force. So this is the work done by the weight force. This would be like the work done by the weight force on the block by the earth. So this part of the packet says that the gravitational force can do positive, negative, or zero work on something depending on how that object moves. Gravity always points down, and remember that positive work means that the object is moving in the same direction that the force is pointing. So if an object is moving down, and we know gravitational force points down, then the gravitational force does positive work in that case. If the object moves up, gravity still points down, and then the gravitational force does negative work. If the object stays at the same level, then there is no change in the position of the object away from the earth. So there is no work done if the object stays at the same horizontal level. If delta H remains constant, then there is no work done by the gravitational force. So here further down the page, the discussion continues, and we said let's consider a ball that begins at height h1 and then ends up at height hf. Regardless of the path the ball takes, the change in energy, or the work due to the gravitational force, only depends on the difference between hi and hf. It does not depend on the path. So this is what we call a conservative force. So the gravitational force is a conservative force. Sideways components of the displacement do not contribute to the work. Now that's not the same situation as the frictional force, because if you were to calculate the frictional force when this ball moved in this trajectory right here, then friction would be doing work on the entire path. So here is our formula for the work done by the gravitational force. It's equal to mg delta h. The work done by the gravitational force when an 8-kilogram bowling ball sitting on a rack falls onto a nearby table will be equal to its mass times gravity times the change in h. Now the ball was moving downwards and gravity points downwards, or the gravitational force points downwards, so this is positive work. The change in the ball's kinetic energy, recall that the work was equal to Fd cosine theta, but it's also equal to the change in kinetic energy. So then if there's 80 joules of work done by the gravitational force, then the change in the ball's kinetic energy must also be 80 joules. And recall that energy cannot be negative. Okay, so energy, kinetic energy especially cannot be negative, because even though velocity can be negative in the 1/2 mv squared, because the v is squared, it will be positive. Now that's not to say that work cannot be negative, because you've clearly seen that work can be negative. The work done by gravity transfers entirely into the change in kinetic energy of the ball. So what is the speed of the ball? Well, if there was 80 joules of work done, that's going to be equal to the delta Ke, which you know is 1/2 mvf squared minus 1/2 mvi squared. If the ball started at rest, this is 0. So we have work is equal to 1/2 mvf squared times 2 divided by m. Vf equals the square root of 2 times work divided by m. Or the square root of 20. 4.47 meters per second. Okay, so we have 80 joules here, 80 joules here, 4.47 meters per second. How much work would it take to put the ball back on the rack? Well, if the work done by the gravitational force to lower the ball was 80 joules, then it'll take me 80 joules to bring that ball back up. And that's positive because I am the applied force pointing in the upward direction and the ball is moving up.